Hello, everyone. Welcome to the Healthcare AI Forum. My name is Gruenloh, host of the forum. Today is my great pleasure to introduce our friends and colleagues from Wisconsin to lead today's discussion. And my friend, Dr. Majid Afshar, he's a tenured associate professor in the Division of Pulmonary and Critical Care Medicine in the Department of Medicine, where he co-leads the Critical Care Data Science Lab for the Department of Medicine. Dr. Afshar is also the director of the Learning Health System in the Institute for Clinical and Translational Research in the School of Medicine. He's part of the UW Health Informatics leadership team and has helped with the implementation and evaluation of emerging technologies in AI. And he helped guide one of the first real-time natural language processing implementations in healthcare practice for clinical decision support, and is leading initiatives to integrate clinical trials and operations for AI interventions. As a physician scientist, his work is dedicated to the prevention and early identification of disease using methods in clinical translation or NLP. Dr. Afshar performs predictive analytics using AI with EHR data for screening and diagnosis of disease in critically ill patients. He has hosted several national data challenges to advance the science in diagnostic decision support and was appointed as a chartered member of the NIH Digital Health and Clinical Informatics Study Section. And he and his colleagues at Wisconsin will bring us topics about agents applied in healthcare, and more particularly, we'll hear about a mixture of agents enhanced large language model, and more agents is all you need, and MDAgents, adaptive collaboration of LLMs for medical decision making. Now, without much further ado, let me turn the stage to Dr. Afshar. Majid, is your stage.
Yeah, thanks, Jan. Emma, did you ready to pull up slides? So welcome, everyone. Thanks for inviting us. We are the Critical Care Data Science Lab, University of Wisconsin, led by myself, Matt Cherpak, and Anup Mayamparath. So we have a journal club session for you guys today. We have three stellar PhD folks. Jifan Gao is our PhD candidate. I think the announcement was a little bit mixed up. So he is our PhD candidate in the Department of Biostatistics and Medical Informatics, and so he's getting his PhD in Biomedical Data Sciences. Emma Croxford is our PhD student in the same program, and Tim Gruenloh is also our PhD student in the same program. And they're all working on variations of EHR predictive analytics using these LLMs and AI methods that are kind of part of our portfolio of work. So they'll be each presenting a paper today. So next slide, Emma. This is our lab that I meant to update. And so the leaders at top, and then we're a pretty big lab in terms of number of data scientists and engineers and computer scientists. Next slide. This is a recent gathering that we just had just for fun. Next slide. Okay, so before we get into these three papers, these papers were presented at big AI conferences, and two of them are general domain, one is medical domain. But I want you guys to think about, large language models, and then people are using this kind of buzzword agents, and what does that mean exactly? So I'll start off by proposing somewhat of a definition here that I don't think there's a clear definition for, but an AI agent is something that really is a system that uses LLMs to interact with the world. They're meant to be adaptive workflows, not necessarily static. And so there are a couple of papers here that kind of offer these things as kind of, LLMs interacting with the world, program that employs AI techniques to perform tasks that typically require human-like intelligence. So what is the difference between a large language model only as a model versus it becoming an agent? Next slide. So a couple of core components that we think are relevant to becoming an agent. One, it needs to make the LLM have perception and be able to observe its environment. It needs to be tasked with something, right? It has to have a specific kind of guidance or task to perform. It can have API calls or interactions with tools outside of its, being able to do web search or being able to do other things. Most importantly, it needs to be able to cache and maintain a memory so that it can continue to use what it's gathered and information it's learning to then further update its knowledge and kind of interact with the other agents or other LLMs. So essentially, it can manage a conversation or something like that using what information is being fed to it and what's being feeding out, and then kind of reiterating on that. And that's probably one of the most important components to an agent system that we are kind of offering here. So without further ado, I'm going to let Emma start first and kind of introduce the first paper, and then we'll go in sequence to Jifan and then Tim, and then we'll hopefully have time for a discussion afterwards and have people kind of run this debate and discussion of, are agentic workflows the future, and what is exactly should be an agent versus just this a special LLM. Emma, go ahead.
Okay, well, hello everyone. My name is Emma. As Majid said, I'm a PhD student here at the University of Wisconsin-Madison. And today I'm talking about the paper, More Agents is All You Need by Lee et al., which was published in October of last year in the Transactions on Machine Learning Research. So to get started, as Majid pointed out, with the agentic approach, you start with a single agent. So in this particular instance, the large language model is the kind of robot figurine here on the slide. You give it a prompt, you get a response. The premise of this paper is there what they term a scaling law to this particular approach, which means can you blow up the number of large language models that you prompt in order to improve your outcomes? So they present what they term agent forest. You give the same prompt to multiple large language models. This could be the exact same model, or it could be a variation of different ones, so you can mix and match some of the high quality ones as well. You then have a response from each of those, and then of those responses, you take the one with the highest similarity score to all the others. So this particular similarity score is not what they get into as much in this particular paper. They leave that up to the specific task or the specific use case that is being used. So in cases where you're generating things like numbers or numerical output, this highest similarity could just be the mode of the responses. Or if you're generating things like text, this could be something with the highest blue score or similarity to the other textual responses. One of the main benefits of this approach as they present it is that you can add on other prompting workflows onto the front. So anything that's maybe more advanced, like chain of thought reasoning, in order to improve it as well. So in order to test this agent forest, they use 3 different tasks. That's an arithmetic reasoning task, a general reasoning task, and a code generation task. They apply it using both open and closed source models. So they have a larger and a smaller llama model for the open source, and then they use GPT 3.5 Turbo and GPT-4 as their closed source models. They also apply 2 different enhancement styles. So as I mentioned before, you can apply prompt engineering onto the prompt before it goes into the large language models. And then they also test it out with doing multi-agent collaboration on the end, which is what my colleagues will be talking about on the other journals papers as well. So to get started, the 3 tasks are outlined here. If you are familiar with those specific tasks, they're labeled under, but in general, the top is if you increase the ensemble size, which is the number of large language models that are being included in that agent forest diagram. Up to 10, you see performance gains. And then the second row is when you get an ensemble size up to 40 is when you start to see those performance gains stabilize. They define these gains through accuracy across all 3 of the metrics defined here. Going forward, they use an ensemble size of 40 for their additional experiments. And so the results that I'll continue to show are all using agent forest with an ensemble size of 40. Except for in the case of multi-agent workflows, these have significantly more overhead, and so therefore they use the 10, which is why they showed both of the results in this way. So as you will see, they show that their agent forest approach has significant improvement gains over just a single query, single agent approach across both the open and closed source models, and across all 3 of the tasks, which are of varying difficulties. They also note that when agent forest is applied to a smaller model, it can achieve similar performance to the same larger version of that model on a single query. And that was one of their key takeaways. They also compare their particular approach to some of the more advanced approaches. So if you're not familiar with the things listed on the left, don't worry. The first three are all advanced prompting approaches. So you have chain of thought reasoning and the like. And then the next two, the debate and the reflection, are both multi-agent collaboration workflows. They show that, again, across all three tasks, that their agent forest approach achieves significant gains compared to just using some of those more advanced approaches. So in this particular instance, this is just agent forest with an ensemble size of 40 is achieving better performance than some of the more advanced approaches. And these results are on GPT 3.5 Turbo. They provide the other ones as well and see the same gains. Finally, they apply the more advanced approaches for prompting and multi-agent workflows along with the agent forest approach, so the combination of the two, because one of their key aspects is that you can apply this with some of the more advanced things on tasks that are a little bit more complicated. They show that you still see gains when you increase the ensemble size up to 40 on the accuracy across all three of the tasks. And in many cases, just the agent forest approach and some of the other ones, when you add on more advanced approaches, achieve about the same accuracy. Some additional insights that they provide when looking at the error analyses for these accuracies is that there are performance gains when the inherent difficulty of a task rises, but at one point these do begin to level off as the increased ensemble size cannot account for the increasing difficulty up to a certain point. They also note that the number of steps in a task helps increase performance. So if you take a larger task and break it down into multiple sub-tasks or sub-steps, then apply agent forest on each step, you see additional performance gains. And then finally, with a higher prior probability task, they also see performance increases. So if you break down a low probability task into multiple high probability tasks, and then apply agent forest on each of those steps, you'll see additional performance increases. Because of this, they present three different approaches at the end of their paper, which is the original agent forest ensembling approach, then the stepwise agent forest approach, which is breaking down the task into multiple steps and then applying agent forest across all those steps before combining them. And then finally, what they call the hierarchical agent forest, which is the probability-based one. So you take a low probability task, break it down into high probability tasks, and then perform those hierarchically in order to get after your final response. The key takeaways is that more agents is all you need, which is the namesake of the paper. They show that increasing ensemble size is able to improve performance, and then also that you're able to combine this with additional methods like collaboration. And with that, I will pass it off to my colleague, Jifan.
Thank you, Emma. My name is Jifan. I'm a PhD candidate at the University of Wisconsin-Madison, and the architecture I'm going to talk about today is called Mixture of Agents. So this paper has been accepted as a spotlight paper at 2025 ICLR conference. Next slide, please. Although large language models have significantly advanced natural language understanding and generation, scaling them up could be quite expensive. When we train the large language models, we require access to massive data sets and thousands of GPUs running for weeks or even for months. And retraining or fine-tuning these models for specific aims brings additional costs of data and computational resources. And recently, the collaborativeness of large language models has been identified, which refers to that a large language model tends to generate better responses when it is presented with output from other models, even if these other models are less capable by themselves. So in this work, the authors propose this architecture that leverages the collaborative strengths of multiple large language models to create a more capable model. Next slide. So the core idea behind the mixture of agents, or MOA, is to structure multiple large language models into layers of agents that iteratively refine and enhance the responses through their collaborations. This architecture consists of multiple intermediate layers and a final output layer. Each intermediate layer contains multiple LLM agents. They all working in parallel. And it starts with the first layer where the original input text is sent to each agent in the first layer. These agents independently generate response based on the input text. And these responses from all the agents in the layer are then concatenated together with the original text input. And this concatenation is passed to the next layer, where a set of agents process the concatenation as the previous layer. This iterative process continues across multiple layers, and the last concatenated output is sent to the output layer, which consists of one single agent, which synthesizes the previous response to produce the final output. Next slide, please. The authors categorize the agent in this framework into two roles: proposers and aggregators. Proposers are the agent in the intermediate layers. Their job is to generate useful reference responses that will serve as the input for the later stages. Next slide, please. And aggregators, on the other hand, are in the output layer. Their role is to synthesize and refine the responses generated by the proposers into a single output. The aggregators, as well as those in the agent in layer 2 and layer 3 in this graph, will be provided with the same prompt with text like you have been provided with a set of responses from various open resource models to the latest query. And your task is to synthesize these responses to a single high-quality response. Next slide, please. The authors leveraged large language models collaboration strengths by introducing additional layers. So the key intuition is that to use the multiple, the intuition is to use the multiple agents in layer 2 and layer 3 to aggregate and refine the previous responses. Then these intermediate aggregations are re-aggregated into the following layers. Next slide. So this mixture of agents architecture is inspired by mixture of experts. So a mixture of experts layer has multiple expert networks with a gating mechanism to select the most relevant experts for the input. Although it is effective, it often requires significant computational resources for training or fine-tuning. And in contrast, a mixture of agent layer combines the role of gating models and expert models into a pre-trained large language model. So this approach can offer two key advantages. It has lower computational cost because it has no need for additional fine-tuning or training. And it has greater flexibility and scalability because it can work with off-the-shelf models, which can be adapted easily to different tasks. Next slide, please. So the authors constructed the default mixture of agents by using these 6 open resource models. They constructed 3 mixture of agent layers and used the same set of models as proposers in each of the layers. They use the Keywin 1.5 as the aggregator in the last layer. And they also developed 2 variants. One is called mixture of agents with GPT-4o, which prioritize high quality outputs by using the GPT-4o as the aggregator in the final layer. And the other is mixture of agents light, which emphasizes cost effectiveness. It uses the same set of models as proposers, but it includes only 2 mixture of agents layers. And the authors validate the architecture using 3 benchmarks. AlphaBack Evo 2.0 evaluates the instruction following and response alignment with human preference. MDAgents assesses multi-turn conversation quality and coherence, and Flask measures LLM performance across different scale dimensions, just like robustness, factuality, and completeness. Next slide, please. And here are the results of our mixture of agents. They mainly evaluate this architecture on Alphabet Evo 2.0 as it is a leading benchmark for assessing the alignment of LLMs with human preference. So the mixture of agents achieves a significant performance boost over the state of the art, which demonstrates it is capable of performing the best performance in this benchmark. And additionally, the MOA light variant designed to, which is designed with only 2 layers for cost efficiency, still beat the state-of-the-art GPT-4o. And next, please. Next. Yeah. And in MDBench, the mixture of agents with GPT-4o secures their top position in the leaderboard, although the margins in improvement is quite small. And in the Flask, the mixture of agents still outperforms the state-of-the-art in 5 of the 2 evaluation metrics. Next, please. In order to understand why the mixture of agents works so well, the authors conducted a series of experiments to analyze its underlying mechanisms. First, they compared the similarity between the aggregator's response and the responses from proposers. What they found is that the aggregator's response tends to have a higher similarity to the best proposer's response, which suggests that it can effectively identify and highlights the strongest aspects of the proposed answers. And they also compared the mixture of agents result to a ranker-based system. The ranker-based system selects only the single best response from a layer rather than passing all the proposed answers to the aggregator. And these results show that the mixture of agents significantly outperforms the simple rankers, which indicates that the aggregator does more than just select the best response. So combining these results, the mixture of agents not only identifies and highlights the best proposed answers, but can also effectively synthesize information from multiple proposals, refining the output for a higher quality. Next slide, please. They also tested the configurations with 1 to 6 agents per layer and compared 2 settings using the same large language model agent in each layer and using different large language models to generate the response. And this table are the winning rates on the Alpaca Evo 2.0. So the higher, the better. These results show a monotonic increase in the performance as the number of agents per layer increased. And using multiple different large language models can consistently lead to better results. So this suggests that having a larger number of diverse agents in each layer can improve the performance. Next, please. They also explored model specialization by evaluating which large language model can perform best in different roles. When evaluating different aggregators, all the 6 open source models serve as the proposers. And when evaluating proposers, the same large language model is used as proposers in all layers, and Kiwin 1.5 serves as the aggregator. So GPT-4 and Kiwin can serve as a versatile role because it can work well in both proposer and aggregator. And Llama 3 and Wizard LLM demonstrated only good performance as a proposer, but they are not effective in aggregators. I guess there's a typo on my text. So Llama 3 is not doing well as an aggregator here. Next slide, please. To conclude, the mixture of agent architecture presents a powerful and scalable approach to improving the model performance through the collaborative and iterative approach. although it may take longer to produce the final output as it needs to go through multiple stages, what makes me feel excited about this work is that it can achieve or outperform state-of-the-art performance across multiple data sets without requiring any additional retraining or fine-tuning process. And with that, I would like to thank you for your time and pass it to Tim.
I'll be presenting this work called MDAgents, and it was presented by MIT as an oral presentation at Neural IPS 2024. So the goal that MDAgents tries to tackle is this task of medical question answering. And that's basically where you have a medical question, and then you feed it through this black box of agents. And then the idea is hopefully you get some sort of good or productive answer out. And as you can imagine, and as you've seen, there's a lot of different ways that you can structure all of these agents such that they accomplish this task. So that's what this MDAgents framework looks at. They introduce a few new ideas that help make their method stand out. But maybe one of the most important ones is this idea of having a complexity checker agent. And that's because this complexity checker is going to decide how difficult or how complex a medical question is. And then based off of what that complexity checker decides, it's going to be fed through different pipelines of agents. So we'll start by going over what this complexity checker actually does. And we're going to be giving it a medical question. So for example, let's say we give it a question that tests medical knowledge. And the LLM checker might say, okay, I have a question that is multiple choice, and maybe I don't need too many different domain knowledges to answer this question. So I'm going to decide that this is a low complexity question. Another example is if we give it a question that asks differential diagnosis, it might say, okay, I don't have a multiple choice question anymore, and I'll probably need multiple domain expertise to understand what the symptoms are and how they relate to different diagnoses. And then the final example I'll give is a multimodal reasoning question. So now the LLM checker might say, okay, I'm back to a multiple choice question, and I do have an image and text which might be difficult to understand, but it might not be super difficult, so I'm going to give it a moderate difficulty problem. So those are the three options that the LLM checker can decide for a problem. It can be low complexity, it can be moderate, and it can be high. And now based off of what this LLM checker says, we're going to have different pipelines to solve the problem because we don't want to overanalyze a simple problem and we don't want to underanalyze a very difficult problem. So what happens if the LLM checker says that this is a low complexity problem? What we're going to do is we're going to recruit a single LLM agent that is a sort of general expert, and it's going to be given the medical query, and it's just going to output an answer, and this is the answer that will be the final answer given back to the user. If the question is deemed as a moderate level difficulty, what's going to happen is we're going to recruit multiple domain experts who are all experts in their own field. And then we're going to give them time to analyze the question. And then they're allowed to talk with other agents to try and convince them that their answer is right. And also discuss the question. And then this discussion will happen for as long as it takes until they reach a consensus or until they reach a max number of rounds. And then all of these discussions are being saved in a log. And then when the discussion ends, that log will be given to a final decision-making agent who will then analyze the question, look at all of the logs, and output a final answer. Finally, if the question is deemed of high difficulty, what's going to happen is we're going to recruit multiple teams of experts, where each team is an expert in one domain, and each team consists of multiple specialists. And then what happens is the medical query gets given sequentially through each team, And each team analyzes the question and generates a report of their findings from that specific domain aspect for that question. And then when it's done, another decision-making agent will look at all of the reports and the question, and then it'll output a final answer to the user. So that's their entire framework here. To recap, you have a medical question, you give that through an agent who decides the complexity, and then based off of that complexity, you can either give it to a single agent, multiple agents, or multiple teams of agents. All right, so let's get into the results now. They evaluate their method pretty extensively on 10 different benchmark data sets. So I'll very briefly go through what each one is. This MedQA data set is a question answering data set on the medical exams. You have a PubMed data set where you're given a PubMed abstract, and then you're asked to answer questions about that abstract. You have DDX Plus, which is a synthetic data set of patients and their symptoms. And then you're asked to choose from a list of diagnosis of what that patient might have. SimCat is another synthetic data set where you have patient symptoms and you need to choose from a list of conditions that that patient might have. JAMA is a real data set taken from a JAMA clinical challenge. And these are some of the most challenging problems that are out of these benchmark data sets. There's these MedBullets data set, which is similar to the MedQA data set, but it was scraped from tweets. So you have medical questions taken from Twitter. And then you have this, now we're getting into the multimodal data sets. So this Path VQA is pathology visual question answering. So you're given an image of a pathology and you're asked to answer questions about it. BMC VQA is similar to the previous one, except it's not limited to pathologies. It's a lot more general. You have Mimic CXR, which is chest radiographs from the Mimic dataset, and you're asked to answer questions about those radiographs. And then finally, we have MedVidQA, which is the only benchmark dataset that involves videos. So you're shown a video, and then you have to answer questions about that video. And the results are, when they compared their MDAgents method with 14 other agent methods, they finished first in 7 out of 10 of the benchmarks. And then if you look at the figure on the right, this shows how their adaptive method performs against only using a single agent and using a group of agents. And their point with this figure is that their adaptive method and their adaptive workflow will typically outperform or perform on par as either the solo or the group methods on all of the benchmark data sets. And then the final image that I'll show you is they did an adaptivity analysis of their LLM checker. So if you remember, this is the LLM agent that decides the complexity of the problem. And we see the adaptive when you use the LLM checker, the accuracy of that, versus when you decide that every single problem is low, every single problem is moderate, and every single problem is high. And if we look at the text-only graph, we see that 64% of the time, the LLM checker classified the problem as highly complex. So this means that even though you're only looking at text, there's probably a lot of different domains that you need to recruit in order to answer this question. And we see that their adaptive method always outperforms the low, moderate, or high only workflows. And then we also have this broken down by image and text. And we can see that for the image plus text modalities, their adaptive method says that the problem is low complexity 55% of the time. So this means that even though you have an image, you probably don't need multiple domains to answer that question about that image as determined by the LLM checker. And then finally, for the video plus text, 87% of the time, the LLM checker said that the problem was low difficulty. So that means very similar to the image plus text. And third point by looking at these is that by using the adaptive LLM checker method, you're able to outperform other types of static workflows. So in summary, they introduced this idea of an LLM checker agent to handle adaptive question answering. And then based off of what that LLM checker says, you can get different teams of agents and different teams of specialists depending on the complexity of that problem. And they performed very well in the benchmarks, performing better than 7 out of 10 of the competing methods. And that's it. So I think we're back to Majid.
Thanks, Tim. All right, so excellent journal club, guys. These are, again, our wonderful candidate, PhD candidate and students in the lab. These papers are kind of, exciting papers to us because they inform some of our own research design. So each of our students here have actually been doing their own type of multiple LLM or multiple agent, however you want to describe it, workflows, and with varying successes. So I think they can speak to some of their experiences. Emma, if you can look at the question answer chat box there was a question about your paper if you want to take a stab at it. This discussion slide is actually kind of a little more provocative in terms of I think it's a buzzword that we throw around a lot in agents and agentic workflows, but is it truly agentic? And that I would follow what Yoav Goldberg says, that being just modular and kind of building these as a programming tool is not necessarily multi-agent. Multi-role is not multi-agent. You can have the same LLM have multiple roles within it. Multi-prompting, multi-model, these are not necessarily multi-agent. I think, again, the thing that we come back to and trying to really push the agenda on what is agentic is being in a mutable state, right? In that these, in the context of LLM-based agents, the mutable state is like having a conversation history. So an agent repeatedly observes, plans, and acts on its own, with its own memory, based on the responses it receives from the external environment, whether that's another agent or outside information being provided to it, like humans and things like that. So I wanted to end with this slide because I think, we can question what is the agentic role for each of these papers and what does it mean to just be an LLM model versus an agent. And hopefully this is thought-provoking for the group and you guys have maybe thought about this yourselves. So we thank you guys for the time. And if you guys wanted to hear more about the individual projects from the students, I'm sure they'd be happy to kind of talk a little bit more about their experiences with trying to do these types of workflows and how they compare to single LLM approaches.
That's great. Thank you so much, Majid, Emma, Jifan, and Tim. And so I see that some of the questions have already been answered in the chat, but also there are a couple other questions. And actually, I think Emma, you are typing an answer to one of the questions, but maybe I can read it out and then you can answer it verbally so that it could save some time and improve some interaction with the audience. So the question is looking at figure 4 in more agents is all you need. We see performance depends on temperature for some tasks, but not others. Naively, I'd expect increasing temperature would always increase performance, though with diminishing returns, provided there are a sufficient number of models to fully sample the possible outputs. Why would increasing temperature decrease performance as seen for the chess?
Mm-hmm. So for the increasing temperature is associated with an increasing sort of creativity for the model, is another way to put it. So it's able to have a more diverse ability to output different things. And so in some tasks, this sort of creativity is not necessary and can actually harm it. So for instance, for chess, you have a subset of possible moves. And so it doesn't need to be too crazy creative like it would for a text-based output, where it needs to generate sentences and create stories or something like that. It's just choosing from the possible outputs. So in the more agents is all you need, their final response is chosen based upon a similarity with the others. So in a more increased temperature, you might get a more diversity of responses, which would mean that your similarity metric is starting to kind of fall apart because it's not being similar to all of them. And so that's what might be shifting it when you have increasing temperature on some tasks.
Thank you. And the next question, and then looking at the timing of the question, I'm guessing it's probably for the last presentation. And so can you clarify the consequence of overanalyzing a simpler question? Is it a question of computational resources or response quality?
Yeah, I think it's both. So like, if you're given a very simple problem and you assign multiple agents to it, you're probably going to overanalyze the problem. I think something similar might happen in real life too. And then on the reverse, and if you're given a super complex problem that needs a lot of different domain knowledge, and you just give it a general agent, it might not be good enough to answer that question. And then, yeah, also the computational efficiency. Of course, you don't want to be spending too much money on API calls. So if you can get away with just using a single agent, then that's good.
I see. Thank you. And the next question is for big picture context. Can these agent model scores be compared to something like the USMLE Step 1 scores?
I think for mine, the USMLE scores, they did it on Step 2/3.
Yeah.
So I don't think they compared it to Step 1 scores.
I guess the question was sort of a general purpose in that probably some benchmarking can be applied to those agent models so that we can have a common ground to evaluate those models and how good they are, and then whether we do have some improvements rather than just the advertisements from different company vendors.
Yeah, so maybe I can step in on that question a little bit. So I think it's twofold. So number one, for question answering on board questions, I think we need to move beyond that task. That task is pretty close to being solved with just a good single LLM model. If you look at Microsoft's MediPrompt paper, for example, they show how just by using some chain of thought with some dynamic few shot, they can get the, I think, Step 1 board questions almost over 90% correct, and outperforming humans. So I don't know. I don't think an agentic workflow is necessary for that type of task. I think where it becomes more useful are kind of more the reasoning situations where a little bit more abstraction is required. It's not simply just pattern recognition or kind of looking at that. You can imagine a med student who studies really well will do fine on board questions, but you throw them into a clinical practice scenario, they'll fail miserably. And so it's more of the kind of multidisciplinary kind of needs or abstractive approaches. And so that's where it remains an open research question on can these agentic workflows kind of help reconcile those tasks, and evaluating those becomes a lot more difficult. So that's very true, because if you can have a task that has a clear ground truth or reference label, and it's a categorical response or like a multiple choice question, A, B, C, D, it's easy enough to evaluate those. But if you're getting one that's coming with kind of a reasoning response and kind of a narrative around a differential diagnosis or kind of a management plan, that requires more of a human evaluation framework. And in that case, actually, Emma has been doing a lot of work on this in partnership and collaboration with our EPIC research team, to kind of really build evaluation frameworks that can get at the kind of summarization tasks of language models, which is more of a narrative form. And so we actually put in the chat box there one of the validated tools that we've just are publishing called the PDSQI9, kind of a follow from the PDQI9 for summarization. And that gets at some of those domains or attributes that are important in this task. But right now, there's kind of this paradox of you need more human evaluators. If you're trying to improve things on our front end and the back end, you're actually causing more labor requirements. And so there is this kind of emerging research field of trying to build judges as kind of automated, separate separately trained LLMs that are aligned with humans and how they would evaluate. But there's a plateau effect on humans too. And I'd see there's an oncology question that's related to this, and that humans can't necessarily agree on a good evaluation, or like, that we have our own limitations and the level of abstraction we perform. So, I think when we looked at this, our intra-class and correlation or intra-rater agreements, between 7 human experts, we can only get as high as around 80% or 80, 0.8 correlation. And so we can't expect LLMs to necessarily, do much better than that either, unless we come up with newer methods or better evaluation criteria. So I think that that's going to remain a challenge, and that is an emerging, evolving field of how do we evaluate these systems that are doing the reasoning and abstraction that is not as straightforward as a question answering or a clear ground truth reference data set.
Thank you, Majid. And the next question actually is from Abel. And since he is here, I'm going to ask Abel to ask a question live.
Great. Yeah. Hey, thanks. Majid, great to see you. Amazing work you guys are doing up in Wisconsin. So mine was sort of like maybe touches on one of the things you said, like what are some of the either successes or challenges you've faced in trying to operate LLMs within a real world environment, a clinical environment? Because I think that's been something that we've been trying to work through a lot of different issues here. So, it's sort of open-ended, but really on the operation of how to get these things into real world data environments.
Yeah. So I think, at Wisconsin, Abel, as you know, we're part of some of the roadmap implementations from Epic on some of their Gen AI use cases, and then we've actually are currently in a clinical trial running ambient AI with a bridge, and we have our own internal house-made applications of classifier models that are kind of like LLM based. And so I'll say this, in our first pilot case that it's also in the literature with UCSD and Stanford, it's our experience, what's called the ART, the automated response technology that Epic has put out for that MyChart message response system that is now, you can run GPT-4 to respond to your MyChart messages, your patient inquiries. The feedback on that internally was, oh, it's doing a good job. It looks like it's appropriate. But what happened in translation to clinical practice is that only got used about 20% of the time across the board. Like we found that kind of utilization rate initially, Stanford found it, UCSD found it, Colorado, all these places all coming out with like, oh yeah, satisfaction is great, the providers like it, but they're only using it 20% of the time. And so we spent a lot of time prompt engineering it and making sure it's getting the right information out and it's factual and all this stuff. But what ended up happening is that we missed the whole ballgame on the human factors design, the whole systems engineering into the workflow. Like, how is it going to be used by the end user, and at what, in what situation is it most useful? And actually, what we found was that when we gave it to the nurse clinicians and kind of doing some of the more straightforward low-level responses, utilization went up to 60% on those cases. And so, there was a system workflow. I always say it's going from prompt engineering to human factors engineering that we missed that gap. And I think the clinical application, we're seeing same thing with the ambient AI. We actually, when we first deployed a bridge, it's a great software and the feedback was strong on it. And, we're still in the clinical trial to actually know how it affects provider fulfillment. But when we first put out, we adjust our workflow. We had to change our standard note template because the way the diagnostic capture was happening off their bridge generated note went from like 80% down to 30%. And it was an easy fix that we just had to rearrange the way we templated our notes so the bridge would populate it where we needed it to, and do it in a way that would provide the information extraction needed for the billers to get the ICD-10 codes out. But it still required that readjustment in the workflow. And it took us a few weeks, but we got back on track. So there's this, the technology, is you have to make sure it's fit for purpose, right? And we can't just find an answer for a problem. We have to identify the problem and see if the answer is the LLM or the Gen AI solution. And so that's not always the case, right? And right now we're still on the provider-facing side, as you know, with clinical decision support, there's issues around regulation and approval. So we're really focusing on some of the augmentation for provider work burden and administrative tasks on our side.
Yeah. Thanks, Majid. Great job.
Yeah, thanks.
That's great. Thank you, Majid. And the next question actually is quite similar to the directions that I wanted to ask. So I probably am going to take the liberty to elaborate the question. So the original question is, what is the process of building these domain expert agents that are involved in the high complexity questions? So, and my elaborations would be for interdisciplinary research and innovation, you might have different specialties collaborating together, whether they are material scientists, the biomedical engineers, and clinicians. And you might want to build agents that are specialized in different tasks. And even in scientific discoveries, you might want to have agents that are good at forming hypotheses, and some are good at crafting experimental plans, and some are good at validation, and so on. So what do you see the field is moving in terms of the agent? Do we get to more specialized agents? It's more like those foundation models, they are trained college graduates, and then with those agents, it could be, you can imagine those are postgraduate programs or training on the field, so that they specialize in different tasks. Are we moving towards that kind of future?
Yeah, that's a great question. And actually, I want to prompt if I'm based on some of the experiments that are being done currently. So Emma, do you want to speak to that on the LLM as a judge and how you are trying to get the human expert and specialist involved in being part of the LLM training? And then Jifan, if you can speak to your multi-agent workflow of how you have an agent for each modality of data from the EHR, if that's okay. So Emma, why don't you kind of explain how you're addressing that?
Mm-hmm. So as Majid mentioned, I'm working on evaluation type things. And so what we did is we kind of created this benchmark PDSQI and had multiple clinicians from different levels of experience that had created the ground truth scores, because that's kind of a difficulty that we run into a lot, is what is the right answer. And we are taking all of those and aggregating them together. And so what we're trying to do is sort of this DPO training alignment, a human preference alignment, in order to push the large language model towards the human responses, and so that it can align with as good as the humans will perform, in order to reduce the amount of time that it takes to do these sort of evaluational things.
Jifan.
Yeah. So my research primarily focuses on the fusion of multimodal EHR data. So the traditional methods to fuse multimodal data is that you need to learn a shared vector space. And when it comes to medical data, due to privacy constraints, people may not be able to access a large amount of data to learn such a space. But in my work, inspired by those mixture of agents architecture, we can leverage those pre-trained large language models to convert those non-text modalities into text modalities, so that multimodal EHR data can be aligned into the text space. That is one of the ways that how we can leverage those agents to convert different modalities into a shared text base. Because text space is natural language, you don't need to learn any additional vector space to do the further alignment. And after combining the text from both the text modality and the non-text modality, you can employ additional agents to either generate your response or make classifications based on your aggregations. So that is one of the ways how we can divide the complicated modality fusion problems by multiple agents through the conversion from non-text modalities into text modalities, which is more intuitive to understand.
That's great. Thank you for the really reflective, thoughtful answer. And then the next question is, what are you doing to mitigate the human factors overlook? You mentioned in response to ABLE, and is there a opportunity to collaborate with human-computer interaction students on future studies and work?
Yeah, that's a great question. So, yeah, we actually have a human factors kind of, as you know, at Wisconsin, Pascal Carrion is kind of pioneer in human factors design, and she wrote the textbook on that. So we've had a lot of people that have come from that school and integrate into our health system workflows. And so we have system engineers and industrial engineers that are focused on human factors design, and they do a lot of process mapping. They do the system engineering initiative for patient safety frameworks, the SEEPS framework and EPIS frameworks, all these implementation frameworks that are kind of brought forward when the time comes to determine if the software is kind of useful for that workflow. And there have been cases where, you know, there was a prediction model that didn't, where we actually realized it was an accurate model. The prediction model had good performance metrics, the way we see publications on ROC curves and all these metrics, but it actually, the users didn't, there wasn't a use for it just yet because there were other issues around the workflow that it wasn't the model's limitation, it was the workflow limitation. And so we have a governance, AI governance committee here called the Clinical AI and Predictive Analytics Committee that kind of first evaluates the prediction models, utility and performance metrics, but then there's that whole other component of translating into a CDS or clinical decision support tool, right? And then that comes the 5 rights of CVS, which brings in a lot of the human factors design components. And if those aren't met, then we're not going to move it forward. And so we've had a handful of these, you know, great models that work well in silo, but the AI chasm where it just kind of falls off in translation does not work. And so we're very mindful of that here. And we have our experts in engineering that help us with that.
That's great perspective, Majid. I really appreciate this practical and operationalizing the AI models in clinical practice. And the last question is actually more of a comment, so that actually doesn't require answering, but I think it will be a good future work that people can keep in mind. So the comment is actually this human low usability is seen across different fields, and people need to be trained to use the system and allow them to use it out of the straitjacked, pre-canned situations. So it has to be adaptive. A nurse has specific immediate needs and anxieties that the AI can help with, and training users is as important as the technology itself. So with that as one of the future directions, I wanted to thank the presenters again, Emma and Jifan and Tim and Majid for bringing us this very impressive and informative set of state-of-the-art works. And so this wraps up this month's session of Healthcare AI Forum. And for next month, we're going to have our friends from UCLA, the West Coast, to talk about the state of the art that they felt impressed with. So until next time, take care, folks, and see you in a month.
Thank you. Bye.
Thank you.